Good morning, class. We're going to be discussing polynomial functions of higher degree. As you can see on this graph right here, we're dealing with just a few. So x squared, x cubed, x to the fourth, x to the fifth, x to the sixth, and x to the seventh. And we'll talk about each of these and their graphing properties later. So first thing we need to do is look at this notes. We have our definitions, key ones that you need to make sure you know: leading coefficient test, repeated zeros and multiplicity, and continuous power function. Test intervals aren't as crucial, but they have the kind of idea that's useful. So instead of looking at decimals for this, we're going to just look at different polynomial functions. And what I want you to notice is that our polynomial functions are all going to have smooth curves. So even if we're changing our, we don't have any b, do we? No, we don't have any b. Okay. So even if a is changing, these graphs are going to have smooth curves. Okay. Even if these change, okay. So even if these a's change, we're going to have smooth curves, okay? So you need to realize that these edges are going to be smooth regardless of what values we have with our different functions, okay? Like if I was to graph a new function, let's just erase all these, and I was just to say, okay, let's plug in a function. Let's plug in a g of x equals, and then let's just say we had a theoretical minus x to the sixth plus x to the fifth minus x to the fourth. So notice that there is definitely curves, smooth curves, even if we have some strange right variation. Okay. Okay. This is still smooth, even if it has some strange variation. Okay. Okay. So we're going to discuss the notes, and let's fill them in. Okay. Our observation is that let's pull this up a little bit. It's at 100. Let's go down. Okay, our observation. Observations. Graphs of polynomial functions produce smooth curves. You know, the years back I taught algebra classes, they thought I was joking when I was talking about smooth curves, but it's crucial. Smooth curves is what tells us it's a polynomial function. Additionally, polynomial functions are continuous, meaning there are no points at which you cannot plug in the x value and find an f of x. Okay, they are continuous in that there's no hole, break, or gap. Okay, we're going to talk briefly about power functions. So before we go into transformations, so continuous means no gaps, holes, or breaks. Okay, pretty simple. There's actually a mathematical answer, but I'm not going to teach you that today. Power functions is any function with y equals x to the n, okay? Where, n is a positive integer. So I'm not going to express this in great detail, but just know it's an element of, let's see if they actually have it. Nope, they don't. yeah, they do. Natural numbers. It'd be natural numbers. Okay. And would be element of the natural numbers. Okay, let's continue. So transformation of polynomials, this is the simple stuff, right? If you're going to have, are you going to have reflection? Then this is where, right, if you have a function, this is a very, very brief overview, so this is going to not go into all the nuances. So this is just, forgive me, but reflection is when A is going to be less than 0, okay? A, or our leading coefficient, leading coefficient, okay, is less than 0. You can also have, you know, vertical stretch / shrink. For polynomials, it's actually not practical to talk about horizontal stretches and shrinks, so it's easier just to talk about vertical / horizontal shifts. Okay, and in this case, it's either h, k. Okay, actually, respectively, it's k, h. Okay. Okay, let's move to leading coefficients. Leading coefficient test is a way for us to look at what changes are going to happen at the end. So the first one, we're going to look at a leading coefficient test for an f of x. For an f of x, f of x is going to equal a sub n x to the n plus, a sub 1 x plus a 2. Okay? There's some patterns. So eventually, when n is odd, okay? If the leading coefficient a sub n is greater than 0, if a sub n is greater than 0, the graph rises to, we always go left, right, falls to the left and rises to the right. Okay, so you can kind of actually think of this as going like this. Weird symbol, but basically it's going to go up and over. Okay, what if a sub n is less than 0? The graph rises to the left and falls to the right. Okay? We're going to look at this case in just a second, but first let's fill in more. Okay, when n is even. Okay, so we looked at when n is odd, when n is even. The leading coefficient, if a sub n, our leading coefficient, is greater than 0, the graph rises to the left and right, okay? And if a sub n is less than 0, the graph falls to the left and right. Okay, let's blow up this so that you guys actually can see. So we're going to look at a graph for this. Okay? So let's look at decimals. So let's look at odds. Okay? Here's our beautiful odd functions, right? A is positive right now, right here. A is positive. So then our graph falls to the left and rises to the right. And as we go more positive, same thing, stays about the same, okay? What about negative? As soon as we go negative, we are flipped, okay? It rises to the left and falls to the right, okay? This just means it's constantly decreasing, okay? As we go left to right, it's decreasing. Okay, that's left, that's negative, and it's positive, okay? What about when we do, okay, so do you understand that? Now let's go to evens. So evens over here are going to rise to the left and rise to the right if it's positive, okay? Doesn't change. What about negatives? Negatives, when the A in front is negative, then we're going to fall to the left and to the right, both falling, okay? So that's for even functions, and odd functions are going to follow their pattern, okay? Okay. Okay, thank you guys so much. We're going to go to the next page.